Hi, I am Eray and this is our Wearable Health Observer project. In order to ensure accurate health observation, we extensively test the data beforehand. Based on our test conducted on some sensors, we decided to replace the sensor. Upon examinations and measurements, it was found that the sensor provides differential output. In order to obtain more accurate readings, it would have required increasing the contact surface, which would have complicated the mechanical design. Therefore, we decided against it. When operating our heart rate sensor in a battery-powered circuit, we encountered issue with analog outputs, leading to incorrect analysis. As a result, we realized the need for a different analog to digital converter (ADS) to address this problem. However, this introduced further complexity to our circuit. Following mismatch between the two sensors mentioned above, we came across the MAX sensor. For the EMU sensor, we initially test our analysis with the cheaper sensor to determine if it would suffice. During the test, we realized the importance of sensitivity in our analyzing, prompting us to invest in the better sensor. After selecting the heart rate sensor, we were able to directly obtain the temperature data. However, for the infrared and red light values, we aim to make the output data more meaningful by regulating the sample count. Also, the purpose of using both red and infrared light in the sensor can be the same. Measuring the oxygen level in the blood requires comparing two values. By comparing the data sets, we could detect the decrease and increases in the oxygen level. However, we had made measurements under insufficient conditions to determine the ratio of accuracy. Since the existing libraries did not support the RTS communication protocol. RTS communication protocol required by our sensor, we attempt to introduce the SPI output of the sensor to different channel and receive SPI formatted data as I2S. This way our data would be more accurate and our communication would be easier. We had to define the generated I2S addresses in the code, where our data reading functions were located, because I2S communication could also simplify our display. With this communication network, we were able to minimize the electronic design by creating minimal number of connections. However, our electronic board was initially planned to be sourced from abroad, but due to the inability to accommodate most of the modules and unavailability of necessary soldering machines, we decided not to take the risk. We ordered the PCB locally and except for a few millimeters of tolerance on each edge. There were no major issues. To connect to the internet, collect data, and implement the necessary functions, we adjust the required libraries based on the sensors. In order to facilitate data processing, we connected the signals and values to MQTT Cloud. All manipulated and unmanipulated data were prepared for integration into our application. The generated data was converted into JSON file format, and every 15 seconds when a heart measurement was complete, it was transmitted to both the cloud and our applications.
Hi, I am Onurcan. Our mechanical design was done within the limitations of sensors, batteries, PCB layouts, and signals. We aimed to create a compact structure to ensure usability. Throughout this process, we made changes to the mechanical design due to sensor and battery replacements. To address weight issues, we transitioned our material from aluminium to filament, which led us to utilize a 3D printer for production. In this context, the produced prototype of the watch is displayed, featuring its assembled state alongside its accompanying components. It should be noted that while further reductions in size were conceivable, it was considered uneconomical due to the escalating costs associated with downsizing individual components. In conclusion, we strive to minimize the dimensions while adhering to practical limitations, achieving the extent of miniaturizations displayed. In this excerpt from our code snippet, you can observe the data acquisition process from the accelerometer, pulse sensor, and temperature sensor. Here you can observe our effort to convert the obtained acceleration data into step count. By comparing peak points and in the acceleration data, we transform it into a step count, which will be utilized in the future for activity recognition purposes. To prevent continuous memory allocations within our system, we retain three sets of data for comparison, subsequently overwriting the oldest set with the next data point. In the given context, our focus lies on the extraction of pulse data through the considerations of peak values. However, due to the proximity of these values, the unintentional inclusion of extraneous data poses a potential challenge during the counting procedure. To further refine data optimizations, we have introduced the implementation of +1 criteria. This criteria serves the purpose of excluding specific values that are deemed irrelevant and should be disregarded within the counting process. By integrating the +1 criterions, we aim to augment the efficiency of our data analysis by ensuring the exclusion of superfluous data points and fostering a more accurate representation of the desired pulse data. Activity classifications has been conducted by analyzing the step count within 15-second durations. This approach allows us to capture the frequency and intensity of physical movements within a short interval. By examining the step count data within this time frame, we gain insights into an individual's activity level and patterns. Using predefined thresholds or machine learning algorithms, we can classify activities such as walking, running, jogging on the step count values. This classification process provides context-aware activity monitoring and analysis.
For software architecture, we will develop a collector software that will collect real-time data. This data will be transferred to database, and through a trainer software, we train and obtain our model to use with real-time datasets. With the real-time data analyzer software, using real-time data in train model, we analyze the data and show results through our GUI. Here you can see our process flowchart. We did exploratory data analysis to understand characteristics of our data. We used pandas, numpy, matplotlib, scikit-learn. We used two different perplexity number, and higher perplexity resulted in better classification results. But as shown in the figures, blue and red dots present sitting and standing, and we had lower accuracy for them. We choose LSTM model. LSTM stands for long short-term memory. LSTM is a type of recurrent neural network designed to handle a sequential data, like time series. LSTM was developed to prevent vanishing gradient problem that is a common problem in traditional RNNs. As shown in the first figure, we obtained model training results. Model loss and accuracy values are stabilized around the values where accuracy is 0.91. As shown in the second figure, we plot loss and accuracy values through training. As shown in the third figure, we plot the confusion metrics to see our model performance for recognizing these three activities. As we predicted at the end of the exploratory data analysis, our model confused between sitting and standing and makes more false classifications with sitting and standing. With datasets, we train our model. At first, we tried 8 hidden layers and obtained figure 1. We failed with 8 hidden layers, and then we tried 32 hidden layers and we obtained 0.94 accuracy. We use Bubble.io to build Who Watch application. User and health professional can sign up and create their profile via Who Watch app. Who Watch app contains a database where we store sensor data that we collected through our Wearable Health Observer smartwatch. We use communication protocol while transferring the data that we collected with Wearable Health Observer smartwatch. After that, we use Bubble Data API plugin to transfer data to our Who Watch application database. We create the data type name user activities that has fields contain information about users' daily activities and general health conditions like heart rate, temperature, and steps. For the standalone application, we use JustNet, Wearable, and Android Studio. First, we obtain our app and emulate it in the Android Studio environment, and then download our application to our phone. Here is a clip of how our application works. We successfully obtained targeted outputs. Total budget spent for this project is 4,570 Turkish liras. Conclusions. Electrical, mechanical, and software architecture are completed. Mechanical analysis and electrical simulation are done. Human activity recognition algorithms are developed and aim accuracy is obtained. Web and standalone applications are built. We create a database for further research. Produce first prototype. We thank you for listening.